Using thin aerofoil theory, the lift coefficient of a NACA 0012 aerofoil placed at 5-degree angle of attack in a uniform flow is. So NACA 0012, so it is symmetrical aerofoil. For symmetrical aerofoil, we know that slope is A is equal to 2 pi per radian. And what will be lift coefficient CL? CL is equal to A slope into angle of attack alpha. So alpha is equal to 5 degree. CL lift coefficient is equal to A into alpha. A is 2 pi, alpha is 5 degree into pi by 180 is equal to pi square by 18. That is equal to 0.55. GATE Aerospace Academy is an institute dedicated to only aerospace engineering. We are providing various courses like GATE Aerospace Classroom Program, GATE Aerospace Online Program, GATE Aerospace Postal Program, and GATE Aerospace Test Series Program. These are our past results, and most of the ranks are from coaching classes only. New batch for GATE Aerospace 25-26 is going to start from 18th February. There is 10% discount for this batch. So if you are looking for good coaching, then you can join us. Next question. An airplane of mass 1000 kg is in a steady level flight with a speed of 50 meter per second. The wing has an elliptical platform with span of 20 meter and platform area 31.4 meter square. Assuming the density of air at that altitude to be 1 kg per meter cube and acceleration due to gravity to be 10 meter per second square, the induced drag on the wing is. So before we find induced drag, first of all we need to find induced drag coefficient, right? So that formula we already know. CDI is equal to CL square upon pi AR for elliptical platform. So first of all we have to find out CL. So velocity V is equal to 50 meter per second, M is equal to 1000 kg, B is equal to 20 meter, and S is equal to 31.4 meter square. So for study level flight, lift is equal to weight, we know, right? So weight is equal to half rho V square S into CL. Let's substitute 1000 into 10 G is equal to half into 1 density V square 50 square into area 31.4 into CL. So we'll get CL is equal to 20,000 divided by 50 square into 31.4 is equal to 8 by 31.4, right? Induced drag coefficient is given by CDI is equal to CL square upon pi AR. AR is aspect ratio. So induced drag we can write half rho V square S into CDI, right? So induced drag DI is equal to half rho V square S into CDI. We can substitute CDI half rho V square S into CL square upon pi AR. Aspect ratio is equal to B square by S. So DI induced drag will be equal to half rho V square S into CL square into S upon pi B square is equal to half rho V square S square CL square upon pi B square. Let's substitute values half into 1 into 50 square into 31.4 square because S is 31.4, 8 square upon 31.4 square into 1 upon 3.14 into 20 square. So di is equal to 63.7 Newton. Induced drag 63.7 Newton. Next question. On day 1, an aircraft flies with a speed of v1 meter per second at an altitude where temperature is T1 Kelvin. On day 2, the same aircraft flies with speed of under root of 1.2 v1 meter per second at an altitude where temperature is 1.2 times of T1. How does the Mach number m2 on day 2 compare with Mach number m1 on day 1? Assume ideal gas behavior for air. Also assume the ratio of specific heat and molecular weight of air to be same on both days. So for case 1, we have velocity v1, temperature T1, Mach number, we can write m1 is equal to v1 by a1, that is under root gamma r T1. Right? This is for case 1, Mach number for case 1. Now for case 2, V2 is under root of 1.2 times V1 and T2 is 1.2 times of T1. M2 is equal to V2 divided by A2. A2 is under root gamma r T2. V2 divided by under root gamma r T2. Now we can substitute V2 and T2 in terms of V1. So M2 is equal to under root 1.2 V1 in place of V2 upon under root gamma r T2, that is 1.2 into T1. So under root 1.2 and 1.2 will get cancelled out. So we have V1 divided by under root gamma r T1, which is exactly equal to M1. So M2 is equal to M1, option D. Next question. Consider a flat plate with sharp leading edge placed in a uniform flow of speed u. The direction of free stream flow is aligned with the plate. Assume that the flow is steady, incompressible and laminar. The thickness of boundary layer at a fixed streamwise location L from the leading edge of the plate is del. Which one of the following correctly describe the variation of del with u? So we know the relationship between thickness of boundary layer del and Reynolds number at any location in case of laminar flow, and that relation is, we have already studied in the class, it's given in formula book also. Del by x is equal to 4.91 Blossius solution under root Rex, means Reynolds number at any location x. Rex is equal to rho v into x divided by mu. So we can write del by x is equal to 4.91. In place of Reynolds number, we can substitute rho Vx divided by mu. So from here, we can write that del is inversely proportional to the square root of free stream velocity. Right? Next question. Consider the following fan flow problem. Flow enters a constant area duct at a temperature of 273 Kelvin and a Mach number of 0.2 and eventually reaches sonic condition. That is, Mach number is equal to 1 due to friction. Assume gamma is equal to 1.4. The static temperature at the location where sonic condition is reached is in Kelvin. So in fan flow, we know that because of the friction, total pressure will decrease, but total temperature remains same, right? Stagnation temperature at both location will be equal, right? So we have Mach number of 0.2 at location 1 and temperature 273 K. From that we can find out stagnation temperature at location 1, and that will be equal to the stagnation temperature at location 2. So we have the relation T01 divided by T1 is equal to 1 plus gamma minus 1 upon 2 m1 square. So T01 divided by 273, that is T1, is equal to 1 plus 1.4 minus 1 upon 2 into m1, that is 0.2 2 square. So we get stagnation temperature T01 is equal to 275.184 Kelvin. The stagnation temperature remains constant, right? That we know that in fan of flow, stagnation temperature remains constant. Means T01 is equal to T02. And that is equal to 275.184 Kelvin. So again we can apply stagnation static relation T02 divided by T2 is equal to 1 plus gamma minus 1 upon 2 m2 square. Now m2 is given, that is 1. So we can substitute m2 value. T02 we already know. We can find out static temperature at that location, right? So let's substitute. So m2 is equal to 1. So T02 divided by T2 is equal to 1 plus 1.4 minus 1 upon 2 into 1 square is equal to 1.2. So T2 is equal to T02 divided by 1.2. 275.184 divided by 1.2 is equal to 229.32 Kelvin. Next question. In the context of study in viscid incompressible flow, consider the superposition of uniform flow with speed u along the positive x-axis from left to right and a source of strength lambda located at the origin. Which one of the following statement is not true regarding the location of stagnation point of the resulting flow? So we have superposition of uniform flow with speed u along the positive x-axis from left to right and a source of strength lambda located at origin, right? So we have half body, right? So stagnation point will be at the left of origin, right? That is true, the option D, correct? And it is also located along the x-axis, that is also true. Option A, option D, both are true, but they are asking which is not true, right? Now option B is it moves closer to the origin for increasing u while lambda is held constant. So what is the formula to calculate stagnation point from the origin point? We have derived in the class and we got Rs, stagnation point location, is equal to lambda divided by 2 pi u, right? So if we increase u, the value of Rs will decrease. It will move closer to the origin, right? It means that option B is correct. It moves closer to the origin for increasing u while lambda is held constant. Option D, it moves closer to the origin for increasing lambda. So from the formula we can see that if we increase the lambda, value of Rs will increase, so it will move away from the origin. So option C is not true. Next question. Shock structures for flow at 3 different Mach numbers over a given wedge are shown in the figure below. Assuming that only weak solutions are possible for the attached oblique shock, which one of the following option is true, right? So we know that when Mach number increases, what happens to the shock angle beta? Beta decreases, right? And what happens when Mach number decreases? These all points we have already discussed in the lecture. We made all points also. So when Mach number decreases, what happens to the beta? Beta increases, right? And after some time, it will get detached. This is for given theta, when theta is constant, right? Because we have 3 variable in theta beta m relation, theta beta m relation. So when theta is constant, when Mach number increases, beta decreases, right? So in all 3 cases, theta is constant. So for M3, it is detached shock, right? It has already detached. So obviously M3 will be smaller. Then for M1, it is attached, right? So we can write M3, then bigger than this. If we increase the Mach number above M3, so slowly it will get attached, right? So at M1 it gets attached. So if we increase the Mach number beyond M1 also, then what happens to the beta? Beta decreases. So for this case, we can see that shock angle is less than this, right? So M2, right? The correct option is M3, then M1, then M2. Next question, air flowing at Mach number m is equal to 2 from left to right accelerates to Mach number is equal to 3. Across the expansion corner as shown in the figure, what is the value of del, the angle between forward and rearward Mach lines in degree? The value of Prandtl-Meyer function are at Mach number 3 it is 49.76 degree. At Mach number 2 it is equal to 26.38 degree. So they are asking this angle, that is fan angle, which we have already discussed in the lecture. Fan angle, right? We also know the relationship between Prandtl-Meyer function after turning and before turning, right? That is after turning, Prandtl-Meyer function for Mach number 3 is equal to Prandtl-Meyer function for Mach number 2 plus theta, right? What is theta? Theta is this, right? So what will be theta from here? Mu 3 minus mu 2. So theta is equal to 49.76 degree minus 26.38 degree is equal to 23.38 degree, right? So we got theta, right? Now what will be this angle? This is mu1, Mach wave angle. What will be this angle? This is mu2, right? So what will be mu1? Sine inverse 1 by m1, that is sine inverse half. M1 is 2, so mu1 is 30 degree. We got mu1 also. What is mu2? That is sine inverse 1 by m2. So sine inverse 1 by m3, that is equal to 19.471 degree, right? Now how to find out the angle between forward and rearward Mach line, known as fan angle? So fan angle is equal to this complete angle, that is mu1 plus theta, minus this angle, it will give us this angle, right? Minus mu2. So let's substitute 30 plus 23.38 degree minus mu2 19.471 degree. So we got 33.91 degree. Option C. Next question. The figure not to scale shows a control volume to estimate the force on the aerofoil with elliptical cross section. Surface 2 and surface 3 are streamlines. The velocity profile are measured at the upstream end, surface 1, and at downstream end, surface 4 of the control volume. The drag coefficient for the aerofoil is defined as CD is equal to drag D divided by half rho u infinity square into C, where D is the drag force on the aerofoil per unit span and rho is the density of the air, right? The static pressure P infinity is constant over the entire surface of the control volume. Assuming the flow to be incompressible, two-dimensional and steady, the CD for the aerofoil is. So we have already discussed this problem in the lecture, right? We found drag per unit span for aerofoil. So that was similar to this only. So we had discussed this problem, right? Where u as a function of y was given. Here also u as a function of y is given. The only difference is in place of small h, they have written capital H D and cross section is elliptical. Chord is C only, right? So what was the drag per unit span which we got in the lecture? I will be directly using that formula which we got in the end, that is the end result. So drag is equal to rho u infinity square h divided by 3. This we got for this case, right? So for the case on the left hand side, it will be same only. In place of small h, we have to write capital HD. Here I am not doing derivation because we have already derived it in the lecture for the case shown on the right hand side, right? So I am using directly the end results. So drag for this elliptical cross section can be written as rho u infinity square HD upon 3, right? So CD is equal to, it's given, that is D divided by half rho u infinity square into C. So that is equal to rho u infinity square HD divided by 3 into 2 divided by rho u infinity square into C. So we got CD is equal to 2HD divided by 3C. So HD is 0.03C. We can substitute. So we get 0.02, right? For the derivation of this end result, drag is equal to rho u infinity square h divided by 3. You can watch the lecture. We have already discussed. So I have used end results directly. Next question. Consider steady incompressible inviscid flow past two aerofoils shown in the figure. The coefficient of pressure at the trailing edge of the aerofoil with finite angle shown in the figure 1 is Cp1, while that at the trailing edge of the aerofoil with cusp shown in the figure 2 is Cp2. Which one of the following option is true? So in one aerofoil, trailing edge angle is finite, and in second aerofoil it is cusp, right? So we know that what happens in both cases we have already discussed. They have already asked in the previous exam also. So for finite angle case, for the first case, trailing edge will be stagnation point because we cannot have two velocity vector at one point, right? So v1 is equal to v2 is equal to 0 and trailing edge will be stagnation point. For second case where aerofoil is cusped at trailing edge, v1 is equal to v2, both have same direction, right? This is according to the Kutta condition. So this time velocity is not equal to 0, but on the upper and lower surface, velocity are equal in magnitude and direction, right? So what is the formula for Cp for incompressible flow? Cp is equal to 1 minus u small u divided by capital U square, right? So for case 1, small u is 0, velocity, local velocity at trailing edge is 0. So we can substitute 1 minus 0 divided by capital U square, where capital U is free stream velocity. So Cp will be 1, right? But for case 2, local velocity is not equal to 0, so Cp will be less than 1. Next question. It is desired to estimate the aerodynamic drag D on a car traveling at a speed of 30 meters per second. 1/3 scale model of the car is tested in a wind tunnel following the principle of dynamic similarity. The drag on the scale model is measured to be dm. The ratio of d by dm is. So here viscous effect will dominate. So we have to equate the Reynolds number. So equating Reynolds number. For model and prototype, rho m Vm Lm for model, rho Vl divided by mu m is equal to rho P Vp Lp for prototype divided by mu P. So rho and mu are constant. So we got Vm Lm is equal to Vp Lp. So we can substitute the values. So Vm is equal to Vp Lp divided by Lm. The ratio Lp by Lm is 3. Vp is 30. So 30 into 3 is equal to 90 meter per second. So drag is proportional to rho L square V square, that is rho AV square, right? So in terms of ratio, we can write dP divided by dm is equal to rho P Lp square Vp square divided by rho m Lm square Vm square. Let's substitute. Rho is constant. Lp by Lm is 3. So 3 square into 30 square divided by Vm, that is 90 square, is equal to 1.